Alrighty. Hello there, everybody. So today we're going to take a deep dive into the world of cardiac physiology. We're going to talk about the heart's electrical system and how it works, how it translates into what we see in an ECG. Also going to be talking about what is happening inside your heart during a heart attack. We're going to take a look at the nervous system, how it influences your heart, and we're also going to take a look at how calcium plays a pivotal role in every heartbeat. Let's get started. The first one is going to be the action potentials of two specific things. First, the SA node. All right, so starting with the SA node, the heart's natural pacemaker. Unlike regular muscle cells, the SA nodes can spontaneously depolarize. So on the graph here, you'll see the pacemaker action potential. So this is the action potential here. So the first phase is phase 4, and this is the slow depolarization phase. And it's what we call the pacemaker potential. It happens because of a funny sodium channel that slowly lets out sodium into the cell. Sorry, that slowly lets in sodium into the cell, and a little calcium via type T channels. And so up here we have at phase 4, we have funny sodium channels and type T calcium channels. That's what's causing it to depolarize. And once the cell hits about negative 40 millivolts, phase 0 kicks in. And that's the actual depolarization. And it's driven by L-type calcium channels, not sodium like in nerves or muscles. And so that's what we see here is the depolarization. And then we have phase 3, which is the repolarization. And that's driven by potassium channels, and those open up, potassium leaves the cell, and the membrane turns around, like the membrane returns to around negative 60 millivolts, and then the cycle starts all over again. Now we're going to talk about ventricular myocyte action potential. Now over here, this one's a little different. Well, actually, it's very different, and we're going to talk about why. So phase 0 is what we're going to start out with. So let's ignore 4 for a minute. 4 is just resting potential. And so phase 0 is a rapid depolarization due to fast sodium channels opening. So that's what we have here. So we see rapid depolarization, like way faster than the other one. And then we get a small dip from phase 1 right here. See, it goes up and then it dips down quite rapidly, but really small. And this is very brief, and it is due to a brief potassium efflux. So we have potassium wanting to come out of the cell there. And we have phase 2, which is unique because it's a plateau phase right here. And we have calcium entering through L-type calcium channels while potassium is leaving at the same time. So we have that um, plateau. And this balance keeps the membrane voltage pretty steady. And then phase 3 obviously is repolarization. We have more potassium leaving the cell. And then in phase 4, we're back to resting potential around negative 90 millivolts. So, how do these action potentials show up on an ECG? And so I have a pre-drawn ECG, right? And I'm just gonna walk through what we're looking at here. So we have the P wave at the first part of this ECG, and that comes from the atrial depolarization. Okay, and then next we have the Q, R, and S complex, and it is a ventricle depolarization. And it's big because the ventricles are so massive. And so that's what we're seeing here. Since the ventricles are extremely big, the depolarization and repolarization are going to be huge. And then the T wave is the ventricle repolarization. And then there is the atrial repolarization. It's there, but it's buried under the Q, R, and S. And so what we're seeing here is the P is going to be atrial depolarization, QRS is ventricle depolarization, and then the T is the atrial repolarization or the ventricle repolarization. All right, now that we understand a little bit about the ECG, let's talk about what is happening during a heart attack using the ECG. So I'm going to show you three ECGs. This one's the normal one. So this is what we expect. This is what we want. Okay, this is what the body, this is homeostasis. This is what the body likes. Okay, now the next one is called a STEMI or a ST elevation myocardial infarction, and it is a full thickness heart muscle injury. So it shows up as an ST segment elevation on the ECG. So as we see right here, we have a normal P wave, we have our Q, and then we have our R, and we see that we don't have an S. So like this one up here, the S wave goes all the way down, but this right here goes slightly down and then curves up with the T wave, which is extremely elevated compared to the normal one, and then it goes back down. Now this is bad, and it indicates a STEMI or the ST elevation injury found within the heart. And now the next one we want to talk about is the NSTEMI or the non-ST elevation MI. And this is usually means that the inner layer of the heart wall is affected and not necessarily the thickness of the heart muscle injury, like full thickness heart muscle injury. This is just affecting the inner wall. So there is no ST elevation, but the heart cells are still damaged. And the blood test will show elevated troponins. And so if we see right here, we have the P wave, goes to the Q, goes to the R, goes down to the S. It's not elevated, but it's also not normal. Okay? And so this is typically what you'll see. It goes to the T and then it goes back. Right? And so this is typically what we see here. Right? So the heart is constantly being influenced by autonomic nervous system. And I split up this whiteboard into two sections, one for the sympathetic nervous system and the parasympathetic nervous system. So we're going to start with norepinephrine. It's going to bind to the B1 receptors, and this is going to cause positive chronotropy, which is faster heart rate, positive inotropy, which is stronger contractile forces, and positive lusitropy, which is faster relaxation. And this works by increasing CAMP, which enhances calcium 2 plus entry and reuptake. So we see as the receptor binds, CAMP increases here. And then when we have the ventricular, it binds, it goes through this entire process up here, but just in a different cell. And we get the calcium, we get a positive inotropy for the calcium, and then we get positive lusitropy as well. Now for the acetylcholine from the parasympathetic system does the opposite. So it binds to M2 receptors, and that slows the heart rate by opening potassium channels, and that reduces CAMP levels. And so I kind of have that illustrated here as acetylcholine binds to the M2, potassium channels open up and causing inhibitory G protein, which then lowers CAMP, opens up sodium, and the L type calcium, uh, calcium 2 plus ion influx as well. So, okay, so calcium is the link between electricity and muscle contraction. Okay, so during phase 2 of the action potential, calcium enters through the L type channel. Okay, as it enters, that small amount triggers much more calcium to be released from the sarcoplasmic reticulum via I think it's ryanodine receptors. And this is calcium-induced calcium release. So that's what that's called. And then, so we have increasing in CCAMP, which helps when we have norepinephrine bind to the B1 receptor or the beta 1 receptors, and the calcium binds, or not, doesn't bind, but this calcium being introduced into the cell induces calcium to be released. That calcium then binds to troponin C, triggering contraction. Okay, so that's how we trigger contraction. To relax the muscle, calcium is pumped back into the sarcoplasmic reticulum through a Serca pump. Okay, and then out of the cell by NCX and PMCA. So now let's look at the cardiac cycle through a pressure volume loop. So we start at the bottom right, over here, and this is an end diastolic volume. So then comes isovolumetric contraction as pressure rises in the y-axis. There is no volume change because all the valves are closed. So we're going to stay on the right. It's going to continue to rise strictly on the y-axis. Next is the aortic valve opens up and we get ventricular ejection, which causes the volume to drop. As we see, it's going left in the x-axis. After that, we hit end systolic volume and we enter isovolumetric relaxation. And again, all valves are closed here. And then finally, the AV valve opens and the ventricle fills again. Okay. Some things to listen for is the first heart sound happens when the AV valve closes, and the second heart sound, S2, comes from the semilunar valves closing. So, to summarize, we've covered how action potentials work in different parts of the heart, what you're seeing on an ECG, and how MIs affect that signal, and how your nervous system tunes your heart, and how calcium drives every single beat of your heart. Plus, we walked through the entire cardiac cycle. Thanks for watching.